This is the Amp Hour Podcast, released September 30th, 2024. Episode 678. All about antennas with Katerina Galitskaya. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Katerina Galitskaya, Senior Antenna Engineer and just antenna enthusiast.
Welcome, Katerina. Thank you for being here.
Thank you for inviting me.
I have been following you on LinkedIn for a while, and you post some of the most intriguing and confusing and magical RF animations. I mean, I just had to reach out and ask you how you understand all this stuff. It's really great.
I don't think I even fully understand now after 10 years work in that, but I think I understand more than most of people. So I post these cool animations and do all the simulations.
Okay, so you post these really great animations. We're going to have links to follow Katerina on LinkedIn as well so that other people can follow along as she posts there. Is this how you kind of see the world as well? Like, I mean, this is a visualization using simulation platforms, but when you look at an antenna on a cell phone, for instance, or a commercial product, do you see radiation patterns?
Oh, yeah, totally. I mean, I have this superpower now. So, yeah, I mean, I don't see it, of course, but I mean, I often think about that. I often think about antennas around me. And if you think, like, for example, just to guess, how many antennas do you think every day, kind of like at any moment you interact with?
Well, my desk is full of cellular modems, so I might be outside the norm, but just as, just normal walking around person, I don't know, 100 maybe. Just thinking about like my Wi-Fi antennas and commercial products and stuff like that.
Yeah, I mean, if you walk around, then maybe
right.
In your
walking
phone,
down the street,
you have at least 10, and then like all the cellular towers, right? On almost every building you have. Yeah, if you walk around, if you have a nice walk, you can encounter, and also you meet all the people that have antennas and smartwatches and everything that doesn't have cables and communicate in some way has antenna in it.
Yeah. So I just bought a commercial product, like an off-the-shelf product, like a security system, basically, that has local recording. I was very excited about that, to not have to pay for a cloud service. But then I realized, so I have a smart doorbell that's now talking through this thing, and it's not then getting piped up to Google like my old house. And instead it's just capturing it locally. But I thought it was going to like sit on my network on Ethernet and I would just tell it the address. But it's like, no, actually, you're going to route all your Wi-Fi traffic through this device as well. And that's actually how it operates. And I'm just like, it just feels like it's so ubiquitous and it's so low cost that is the spectrum just a mess these days?
Yeah.
Especially 2.4, 5 gigahertz?
Yeah, exactly. 2.4 is quite a mess, especially you don't only have Wi-Fi there, you also have Bluetooth and also some other devices like IoT devices. They work on this. It's called free spectrum,
threads
right?
In 2.4,
yeah. So 2.4, like it's free. Everybody can use it. And so that's why it's good to have, and now like a lot of companies, they include Wi-Fi 6, Wi-Fi 6E, Wi-Fi 7, so it broader bands, and also 5 gigahertz bands. So it's always good to have some diversity.
Yeah, it's getting overwhelming sometimes. I mean, it depends, I guess, on the day and whatever. But I have a board that I designed that has a ESP32C3 on it, and it's got a 9160, an NRF 9160. So like right there, that's GPS, LTE-M, and then 2.4 gigahertz. I don't think it does 5 gigahertz. So that's at least 3 bands, and then associated antennas. And and to be completely honest, most of the time I kind of just punt and I just say, well, someone else can do this. And I put a SMA connector or a UFL connector on there. And I say, someone else has done the antenna stuff. I don't even want to touch that. Right. So,
but I actually think that's the smartest approach, because usually you don't want to touch antenna if you don't understand what to do with that. Better to leave into antenna designer because then you will do some mistake and they will hate you.
You're right, exactly. Yeah, the iPhone 4, was it iPhone 4? Was that the one where it like coupled to people's skulls or their hands or something? I remember there was one.
Yeah, I remember something like that. I think also iPhone 12 was a total disaster because it worked badly if you hold it in the wrong way, according to Apple, of course. But
Right.
yeah, it's always user mistake, right? It's always
Right,
user mistake.
of course. And yeah, so that's a maybe a good focal point. I guess that's a very complex device. But something like that, where it's multi-band, it's multi-radio, multi-protocol, where do you even start with something like that? How do you start to construct a simulation to even maximize the output there?
Yeah, so mobile phone is a good example for that, right? You need a lot of cellular antennas there, and also you need diversity, so you cannot just put one cellular antenna, because you need polarization diversity to connect with to base station antenna in every like position of your device. You can hold it in different ways, right? But yeah, in case something blocks one antenna, you really don't want to lose all the connection. You want to have some backup antenna or something. And also to enable MIMO, you need several antennas. And then you have, of course, Wi-Fi, then you have GPS, then you have ultra-wideband antennas now in new phones. And then you have NFC. Some people don't think that it's antenna because it's very low frequency, but it's still antenna, kind of like principle, right? It works in a near field, but it still radiates. So yeah, usually you start with very simple design, imagining your phone as a kind of just a like PCB metal block, right? You have just ground plane with the size of your phone, for example, 30 times 100 millimeters or something like that. I don't know. And you start to think first with the cellular antennas, because they are the most challenging, because they work on the lower frequencies. So, for example, 600 megahertz, 700 megahertz, that is the lower band of cellular connection.
And lower's harder, you're saying?
Yeah, harder.
Interesting.
Really harder, because they require bigger ground plane to work, to radiate efficiently. So antenna, this kind of antennas that we have in our devices, they never. So antenna is just like you can imagine it. I don't know how you imagine it, but probably like a wire, right? Like some wire. Yeah. But this wire, it needs some feed point. And after this feed point, it also needs some ground plane. And that ground plane works as extension of antenna. You can imagine, so if wire is a monopole, so this ground plane is also monopole, and it makes dipole. And this is what works, this dipole that radiates, not only monopole. So yeah, so
just to put a finer point on that. So if I visualize, actually, I always think about the little LoRa boards. Like I buy one from Adafruit, and it doesn't have an antenna with it, and it's just like, no, just solder like a roughly 3-inch wire on here. Yeah, it's good enough. It's about 900 megahertz. That is my visualization of a monopole, right? Like the cheapest, kind of crappiest version of
but
that as I
you
can.
always need to connect it to something. You cannot radiate from thin air, right? You need to connect, and that connection will have this extension of the other part of the antenna. That connection will have this other part. So in our, or before you were mentioning this PCB that you're working with the ESP modules, and on that you have antennas. These antennas, they don't work just because they work because you connect them to your ground plane on your PCB. So if you didn't have a PCB there, like metal, that antenna connected to, this antenna is just in the air, like in the vacuum, right? Like hanging in the air, it would never work.
Got it. Yeah. So when you visualize stuff, are you visualizing like a satellite in space, because it is like a vacuum floating in, floating in the void kind of thing? So you're saying though, with a dipole, if you just had two lengths of wire and you had like a center feed on it, that would work. But a monopole does not work.
Yeah, the monopole, you need to feed it from somewhere. Monopole, it will radiate around it, but you need a feed point to that, of course. And also monopole is much, much bigger. So dipole is twice smaller than monopole.
Got it.
So all the antennas that we have in our consumer electronics, we tend to make it as small as possible, right? And for that, we need to kind of like make them like meandering, or use just a fraction of wavelength, and construct antenna like on the very, very limited space. And that is just what I'm explaining now, is just the antenna part. So basically the radiator that kind of like focus the signal in itself, but it will never work without being connected to PCB or like ground plane. It of course depends a lot on antenna type. Different antennas require different, but if we're now talking about like really common, like some PCB antennas, right? Or as well in our mobile phones, it's not PCB antennas there. It's most probably some 3D shapes antenna because we really need to use all the spaces. But they also connected to ground plane. And returning back to why lower frequencies is harder, because we want to keep devices small as possible, but the lower the frequency, the longer the wavelength. And we always want to have our PCB size half of the wavelength on both antenna and ground plane. So on the ground plane, we need at least quarter wavelength then, if we kind of split it equally between antenna and ground plane. And then when you calculate that for lower frequencies, you need at least 180 millimeters or so. And if you don't have that, then you just decrease efficiency of your antenna. Like you cannot fix that. This is just physics. There is no way around that.
There's no like better antenna fractal design, nothing like that matters.
Nothing will help if you don't have enough PCB size.
Got it. I do think throughout this episode, it might be interesting to have just kind of easy rules, which are obviously meant to be broken and or confirmed with an expert such as yourself. But that PCB size is a really great one, right? So you said 180 millimeters. Was that for a specific wavelength, or is that just
that is no. That is for, it comes from wavelength. So
got it.
It's better to remember it's like that. That for if we are talking now about just some PCB antennas, right? For example, inverted F antenna. This is very popular, right? Inverted F antenna. You always see it on ESP,
low
like
cost
32.
ESP boards.
Yeah, exactly. ESP. It's always.
How do we make it lower cost? We make the antenna out of the copper that's on the PCB.
Yes. So this PCB antennas, they need a quarter wavelength ground plane. For 2.4 gigahertz, it's around 33 millimeters.
And
this is just ground plane.
Surface area, or that is length?
Length. Length. You have antenna part, and then down from the antenna, it's a length. That's why it's also very important to place your antenna so that you can have very efficient way of using this ground plane. For example, if you have PCB that is short on one side and long on another side, you want to place your antenna on the shorter side so you can use this long ground plane. So.
Interesting. Okay, that's another great. Okay, so these are kind of the tips that are coming out of here now. So it's obviously have a large enough PCB plane or ground plane rather, but then also place the antenna on the short side, or take advantage of the length.
Exactly. Always place the antenna on the shorter side of the PCB, and better in the corner, and always on the edge, never in the center of PCB.
Yes.
For the love of everything, I don't know how many times I need to suffer and see on some internet some design where people place like ESP model with a IFA in the center of PCB.
We did a cutout though. There's a cutout in the middle of the PCB.
Yeah, I mean this is actually good case if they have cutout.
Okay. So better than nothing, but not great.
No. I mean it's still very bad, but I think that it's not always that you see that people who place antenna in the middle of PCB, they also thought about cutout. Usually they don't think about antenna at all, and they think that you can place it anywhere.
Right. They think it's easier routing for my signals, my low and slow signals, if I turn this module 180 degrees and the antenna's in the middle of the board.
Yeah, exactly, because it's easy, right, to place, I guess, to route and everything. But yes, always place it on the edge, always place it better on the shorter side, and always have a good keep out area, so no metal below antenna on any layer. On any layer. Yes. And usually if you work with some, like for example, ESP model, they always have guidelines, right? Just follow the guidelines for antenna, for like footprint, because you usually want to have some bigger keep out area than antenna itself, just to be on the safe side. And don't place any metal components, like big components. Sometimes you have some big capacitors. Sometimes you have like USB port, for example, or something like that.
Right.
Just don't place it near the antenna. Choose some other place.
Yep. Yeah, actually, you have a recent post that we'll link in that's a really good example of kind of all the things not to do. It's pretty great. Yeah.
Yeah.
How often are people approaching you with this sort of thing? Like, I mean, I imagine you could look at something like this and just snap, no, that's not right, like that sort of thing.
Yeah, I usually spend like maybe 10 minutes per week just scrolling. I have several hashtags on LinkedIn like ESP32, PCB
Oh, yeah.
design, and just
Yeah.
scrolling like people post their designs. And sometimes I just give some guidance because in 90% of the cases, people already know some generic guidelines and they just
Yeah.
maybe need some recommendation. For example, if they have two antennas, what is the best way to place two antennas so they don't couple to each other? So the best way, right? Or maybe in this case, better to turn antenna 90 degrees and place it on the shorter side. But yeah, sometimes you see something like very outrageous. The antenna is placed in the middle of the PCB and there is no clearance area. There is metal below it and all the metal stuff around it. So yeah, that's sometimes it happens as well.
Yeah. I actually gave a talk back in 2019 when I was starting to do some of these my own designs, but I actually followed a different talk from a past guest of the show, Mike Osman, who did the Hack RF1. And he gave five rules for his stuff. And I just follow that. And I've been relatively successful from that. But that's actually most of the time then like I said, I just kind of let someone else do the actual antenna piece. And I'm just really designing the board to follow, like, it's basically like the guidelines you mentioned in the PCB, or sorry, in the data sheet. I'm just kind of using these as a data sheet guideline for the PCB itself.
Yeah, I think that for these 2.4 antennas, they are quite forgiving if you just follow these guidelines, right? You have clearance and you don't design actual antenna yourself, maybe because for that you need simulation. But if you already have footprint for antenna, if you have actually like radio antenna, for example, you have ESP32 model, then you just follow the guidelines and you can place it yourself, even if you're not antenna engineer. For everything that is more complex than 2.4 IFA, yeah, I would rather go to antenna engineer because then like, so now I work mostly with the base station antennas, but 1 year ago I worked with just customer electronics, like all the wireless devices that you can imagine, phones, headphones, routers, like everything. I designed antennas for them, for that. And yeah, it's how you can understand if the project manager or is the owner of the business is good, right? They come in the beginning to you. And in like maybe 30% cases, people already come when they fail once because they thought that they can manage this themselves.
How hard could it be, right?
Yeah, they didn't pass certification, or they didn't even get any signal or something. And then okay, so the antenna part, maybe it's not so easy. And then they come to company that's like design antennas. And then in this case, it's always like, okay, you already have a device. You cannot even change a lot of things, right? Because they really don't want to spend even more money on changing all the things. But sometimes, because you kind of left antenna part on the very last, you have very bad location. You have very bad design, PCB design. You don't have enough space or whatever. So if you come in the beginning, if you think about antenna in the beginning, you take that into account, all the things needed for antenna.
Right. I mean, I can imagine even at the mechanical level, like of, leave this region, just to go back to the phone example, we're going to have someone holding this in their hand. So like, think about the hand. We need to model, a piece of meat on the back of this phone that might be absorbing signals. Right?
For sure. It's always like next thing, but it may be more advanced. So we just gave some tips for example, PCB engineers, right, who want to just put, for example, ESP32 model to the antenna. So for them, these tips are enough. Just to keep antenna clearance, keep it on the shorter side of the PCB and on the edge. I think that will be enough, and you will get good efficiency from your antenna.
80% of the way there, right?
Yeah, exactly. And you will at least have, for 2.4 gigahertz, it's quite forgiving, so you will get signal. But then if you like one step further, then you think about where your device will be. Because if it's on the ground, that's one case. If it's hanging in the air, that's another thing. If it's in your hand, that's third thing. If it's mounted on some metal plane, it's another thing. And that's called antenna environment. And that is really important because it changes, and in some cases significantly change how antenna behaves. And you cannot anymore use that antenna that was kind of, you thought about it as it was like in the vacuum, and
Yeah,
then
yeah,
you take it in your hand and it's not the same antenna anymore.
yeah. What could you rank easiest to hardest in terms of the antenna environment?
The hardest is underwater, I would think. And
Oh,
then
really? Oh, okay.
well, think about some like this underwater communication. You cannot communicate there. Like there is water
Yeah, yeah.
absorbs 99.99% of signal. There is nothing. Like you
Mm,
cannot. That's why all these underwater things, they try to invent some new things. I don't know,
right.
communicate with light or something like lasers. I don't know,
Yeah,
like,
yeah.
but not
Right,
the
right.
radio frequencies.
Right. Yeah, and I think if they do a lot, obviously a lot of sound, right? Like low frequency stuff will travel
Yeah,
through water, right? But
yeah,
it's
maybe
still
maybe
low
sound.
bandwidth at that point.
Yeah,
It doesn't really
exactly.
help.
To be honest, I don't know. I just recently read some article about some new approach that's testing for this submarine kind of communication, but it's
Hmm.
not radio frequencies. And next one, I would say human
Oh, really?
body,
Oh, wow. Okay.
because it's, well, we kind of
Big
coming
bags of
from
salt water.
100% water. Yeah,
Yeah.
now we
Yeah.
come to 80% water. So yeah,
Yeah.
it's very challenging, and you always need to take into account your user case in this sense. Then a lot of things coming from that. So first of all people are different, fat tissue different,
Hmm.
and between people, and also between part of the body. So if
Sure.
you have a
Yeah.
head, for example, head bone, you have one like structure that's close to your device. And then if you have some device that is on the belt, for example, that's another environment.
So it's like a
Or
fashion choice too, if you like wearing your cell phone
yeah.
on your belt or not.
I don't know. I don't know. It's just some like GPS tracker or
Yeah.
something like.
Yeah.
And
Yeah.
I designed a device like that. Just it was
Oh,
some
interesting.
like GPS tracker, I think, for older people, and they just put it on their belt, like just clip
Oh,
it
sure.
kind of.
Sure. Yeah. Yeah.
And then you, for example, smartwatch in on the wrist. Then I don't know, a lot of things. And then also implantable antennas. It's
Mm.
inside the body. So you have a lot of cases, and you need to really simulate and design your concept taking into account that. So
Mm.
how usually you work with that is you start with the vacuum. You start with the just like very very simplified design, and you at least like design something. Okay, I choose this type of antenna. So you make some very initial decisions about your future design. And then after you kind of have the concept, you really need to, as soon as possible, start to work with the environment. So for example, if it's phone, then
Got it.
primarily it will be in hand and near your head. And then you include that part in the simulation, and you simulate with that, because human body will like absorb and reflect, depending on frequency, a lot of signal. And then it also can even change frequency of antenna. So you really need to kind of take into account. Yeah, and after that you need to prototype. And when you have your prototype, it's not the you cannot anymore to just measure it in the vacuum, because it's like just hanging in the air, right? Because it's
Right.
already
Right.
not the same antenna. You tune it to work on the body. So you need human dummies. There are a lot of things in the labs that kind of human head, a bit
Oh,
kind of
really?
creepy
Okay. Yeah.
Halloweenish feelings. You have
Wow.
hands, you have heads, you have the
It's
torso
like a body
parts.
part factory.
Yeah, exactly. And it's
Wow.
like they are very heavy because they have this liquid that imitates tissue, right?
Oh,
So,
wow. Wow.
and you just mount your prototype on that and hope for the best. This is like one challenge, right? And the second challenge is that when it comes to humans, we have a lot of safety regulations. And we
Yeah.
have a lot of certifications. You cannot just blast signal towards humans with whatever power you want. You need to, it's called SAR, so specific absorption rate. And we
Okay.
have this limit that regulates, for example, like for 1 gram of tissue, we have this power of signal maximum that can come to. And then you need to, of course, adjust your device, adjust your total radiated power, for example, or adjust the efficiency of your antenna so you don't go over it. And then when you kind of adjust for that, you also need to pass certification for operators, for example, if you want to have cellular connection.
Sure.
And
Sure.
for that, you want to have more efficiency and you want to have more radiated power because they have limits. And so you need to really like balance between those. You cannot have too much, but you also cannot have too low. And you need to be like really in the sweet spot.
Thread the needle, huh? Yeah.
Yeah.
Well, and one thing that seems difficult from just what I've seen of, the testing side of things too, is that you only have like 1 or 2 dimensionality in the testing capability too, right? So you have these wonderful visualizations that are from the simulation models, but you don't get to see that unless you have multiple probe points in an area, right? What does it actually look like when you're in the lab measuring this stuff?
Yeah, exactly. So this animations, it's like fields we cannot see. I mean, now I think some companies, at least I saw some advertisement that they have some scanners, like field scanners that you can kind of like artificial reality kind of, so you can see the fields.
Got it.
But I don't know, maybe
seems like something that a CEO would buy at like a testing company and like promote it, but then it'd be like, the engineers would be like, this isn't that useful for us.
Exactly. That's what I wanted to say, but I don't know how useful it is.
Yeah.
We have another metrics in lab, right? We have network analyzer that we see the reflections, so we can judge how good antenna matched to the input. Usually it's 50 ohm input impedance. So we judge that. And by that, we know how good our antenna receive signal from the chip, right? From the PCB. So that metrics. And then over the air measurements. So they call like that, over the air measurement. So we have anechoic chamber. If you ever seen this, like a lot of small kind of triangles.
Pointy things on the wall.
Yeah,
right?
pointy things. Yes, pointy things. So in an anechoic chamber, you can measure how antenna actually radiates. And from that, you get total radiated power and efficiency. And you also can build cuts of radiation pattern, and even you can have this 3D radiation pattern. So it all depends on how it all depends on how long time you want to spend to measure these cuts, because you need turn antenna like every degree or so and measure on that. So
got it. Yeah, because there's always like the rotating tables too, right?
Yeah,
like
exactly.
You rotate the product, or you have got it. Yeah. So that's kind of what I'm thinking about is, so we have these visualizations with the different field strengths that we're visualizing with different colors and shapes and lobes and all that stuff. But then when you get into the lab, you have to then just step the antenna like 1 meter from the product and then 1.1 meter from the product, right? If you wanted to have the equivalent kind of remapping, you would have to have multi-step tables or multi-step measurements and then reconstruct it from those, correct?
I don't quite understand what kind of product you mean. Like we have antenna, and in anechoic chamber there is no product. Like antenna does not connect to anything. It's just we have like default antennas there. That's
well, it's a second antenna that's actually receiving.
Yeah, second
from the first
antenna
antenna,
that
right?
receives. Second antenna that's we have it measured. We know how it works, and we can judge by that antenna our antenna.
Yeah. So what I was saying is, to perfectly replicate a simulation, like a visualization simulation type thing, wouldn't you need infinite antennas at different points around a room?
You mean some like probes in every point? I guess. And I know that there are this kind of scanners that do that, but not for antennas, because it kind of doesn't make sense. You don't even need that. But I know that there are these kind of scanners that scan PCBs for EMC issues, right? Then you can see kind of visually where you can have some potentially EMC issue or something like that. But for antenna, it doesn't make sense. Like these metrics that I just described, like VNA, passive measurements and then over-the-air measurements in anechoic chamber, that's more than enough for antenna testing. Sometimes when we have cellular antennas, we also have some active measurements. So when actually our antenna receives signal, and this called and sends signal, so like actively working, not passively working. That's also, but that's very rarely when it happens, because like 99% you can do everything with the passive measurements and kind of confirm that your antenna works.
Got it. What does it look like on the flip side for the calibrator? What are the people that work in a calibration lab called? Like a measurement engineer?
Test engineers?
Yeah, they test it. Yeah, I guess so. What does it look like to make sure, because you're saying that you're designing a custom antenna and then it is transmitting to a reference antenna.
Yeah.
How do they know that is good? Like
reference
always that
antenna,
calibration
problem? It's calibration, and you buy it from good vendors that provide all the data about this antenna, and then you calibrate it in your chamber, in your environment, and that's how you know. And sometimes you can also see it in your measurements when something is wrong. For example, you get efficiency more than 100%. It's good. I would like that in every case, but then maybe I need to be a bit suspicious. Maybe I don't need to believe it, even though I would want to, but
just ship off the report and say, boss, I deserve a raise.
Yes, and a Nobel Prize.
Yeah, right. That's interesting. So we're at the point now. So we've kind of walked through some of the guidelines around it and maybe some of the testing stuff here. But I guess one question I had is, aside from talking to an antenna engineer and putting a custom antenna on board, is there a guideline for when I should even be considering to do that sort of thing? Do you have kind of high-level guidance on when to go antenna down?
Yeah.
Or,
I understand your question. So I would say that if you use, for example, cheap antenna, right, off-the-shelf antenna, you need to always check the data sheet. And in this data sheet, it always says what is the reference board for this antenna.
Okay.
And then you also have a lot of plots, all the efficiency, all the nice things there, but all of that only guaranteed on this reference board. If you have anything, and that reference board is exactly quarter wavelength.
Yes, right.
So if you have anything that is significantly different from that, I don't say 5 millimeter different but significantly. For example, you have round shape of the PCB or you have twice smaller PCB. This antenna won't work like they show 100%. I guarantee that it will not work as they show in this data sheet. And in this case, I guess it also then depends on frequency. If you want to work on the lower frequency or you have multi-band antenna, then I would really suggest to have some consultation, at least consultation with somebody who understands antenna.
Yeah, I've been really surprised. I looked at a GPS module and then I was like, oh, okay, what are the options for an antenna here? And then I think it was just on DigiKey. It was just a little teeny tiny ceramic antenna. I'm like, there is no way.
Ceramic. Because they work quite good. Most of the GPS antenna they make in this ceramic because it's quite low frequency, right? If you think about it, it's 1.5.
Yeah, I didn't. But I'm just thinking of the size of the antenna itself.
Yeah, size of the antenna, because ceramics is super high dielectric constant, and the higher dielectric constant you have, like substrate, right? So usually you use FR4, the cheapest one, and it has 4.4 dielectric constant epsilon. So if you put your antenna on that, so wavelength decrease in the proportion of this epsilon. So the higher epsilon you have, the smaller antenna you need. But also efficiency suffers from that as well, but it's another story.
Okay.
So if we go with the smaller, we want if we want the smallest antenna, we would take the highest epsilon, so highest dielectric constant. And those antennas, those GPS antenna, they have really high epsilon, 10, 20.
Oh, wow. Okay.
That's why they can put just some metal dot and it works.
Got it. Okay. All right. So that's yeah. All right. That's maybe I was just off base. Like that's the thing. Like I don't. I'm basically like you said, looking at reference platforms and kind of
Yeah, but
deciding
you're
off
already
that sort of
doing
thing.
more than some people, because some people don't even look at these references. So yeah, I would
Got it.
say if you would just deal with a 2.4 antenna, some kind of like PCB antenna, probably you can do it yourself if you have
Mm,
experience in PCB design, right? You
mm,
can read the guidelines, you can understand the guidelines. Probably you will manage.
got it. Okay.
2.4 is very forgiving. Yeah.
So the real question then is, am I going to try and build the antenna myself in the PCB? That's where you really should be asking yourself tough questions around that sort of thing
Yeah, I
versus buying
wouldn't.
off the
I
shelf.
think I wouldn't do that
Okay.
if I were like PCB designer.
I've actually been really surprised on the 2.4. So just to stick with the espressive example, I've been seeing a lot more designs go away from inverted F on a PCB, and instead they follow with that bent metal. It's still super low cost because it's just like a stamped metal piece that gets inserted, but it's basically like a folded inverted F, it feels like, that gets soldered into the board that's
Ah, you mean
lower.
like 3D shape? Kind of you don't put it on.
Yeah.
Yeah, it's still the same type of antenna. It's still inverted
Sure.
F
Yeah.
antenna. It's just like in 3D dimension, kind of. So
Got it.
in
Got it.
three. Yeah.
So there's no like inherent value there other than maybe allowing you to have a smaller board shape, that sort of
No, I
thing.
think, yeah, I think no, you won't get any more benefits from that because it still comes from size of your ground plane.
Got it. Yeah.
But
Okay.
you can, yeah, maybe like use smaller PCB space on the antenna itself, and thus you have smaller PCB size if you want to achieve that.
Got it.
And also
Okay.
if you maybe cannot allow to have anything on the PCB, but you have space above PCB, right? So you can place antenna there. It's all
Sure.
like sometimes it's quite beneficial to have some 3D printed. It's also like this laser technology, if you know, it's called like LDS, that you can
Oh,
like
sure.
print
Yeah.
antenna on the, for example, plastic cover. If you saw not this post, but last week post, I posted about new AirPods, and they have
Yes.
exactly
Yeah.
this LDS technology and antenna. Like I showed there how this antenna looks like. So they basically printed it inside, and it's some funny 3D shaped antenna. That
Hmm.
because this is such a small device, right? You really don't have any place to put antenna, and you need good antenna because it's human body. You have a lot of challenges, and they solved it by printing this unique shape 3D shape antenna.
Yeah. I think that's the same one. I don't know if you watch the Applied Science channel, but Ben Krasno did some experiments where he was doing his own laser sintering and stuff like that to try and replicate that process. But I think
Mhm.
it is almost always targeted at those 3D antennas for these
Yeah,
applications.
yeah,
What does the feed look like for something like that? You still have to
yeah. It's
connect it.
usually it's kind
Yeah.
of some like spring from that goes from like
Okay.
PCB, and
Hmm.
it's usually has some pressure, kind of, so
Okay.
it's kind of
All
like
right.
spring with the pressure, and you then, or it can be also pogo spring. So there are options
Got
to
it.
feed that. Yeah.
Got it. Okay, so you had mentioned some of the MIMO stuff and like some of the newer technologies are also doing like beamforming and things like
Yeah.
that.
Yeah.
So, what should, I guess, thinking about our audience is a lot of PCB designers and stuff like that. What should they be thinking of do come out that have beamforming, beam steering on board and things like that?
This is very advanced.
Okay,
So
so definitely call Katerina. Okay, at that point, yeah.
yeah.
Okay.
Yeah, this is very advanced. So it's very, how to say, so with the beamforming, you always have a lot of antennas. So it's array of antennas, right? We cannot beamform from one antenna because you need some shift in phase between antennas to steer beam. And also one antenna has very very wide radiation pattern, just radiate everywhere usually. So for example, if you imagine dipole or monopole, it's just like around everywhere, or omnidirectional so called.
Hmm.
That's
Hmm.
what we want in our, for example, rotor. We want it to radiate everywhere, so we have a good signal in the bedroom, in the bathroom,
Hmm.
everywhere.
Yep.
Then when we come into beamforming, we want very narrow beam, so we can point into direction and deliver signal, very very high concentrated signal, only to this point, not to other points that's maybe near it. So if you can imagine like just some beam that is focused, for example laser, right? It's focused beam of light, and the same with their RF signal, we can just focus it into one direction. and transmit some very high power data to the person who receives that signal, or antenna who receives that signal. And this is what all the base station antenna are doing. They have beamforming because the antennas are placed, the base station antennas, they are placed somewhere high on the buildings, right? And then you don't have people there like hanging in the skies, so you don't need to transmit signal there. You really need to transmit signal
Right.
towards the house, for example, that's there, or towards street. And that's how you have a lot of antennas there in this base station antenna, and they all combine together and create one beam, and then you steer it. Some antennas steer mechanically, so actually turning mechanically, but it's not so used nowadays. It's usually like
right.
actually
old
steering,
satellite
like beamforming.
dishes.
Yeah, exactly. So this is actually like actual beamforming that is used now. So you can send your signal there when you know it will be used, because you don't want to just blast the power to nowhere, kind of.
Okay. All right. And you had said it's very advanced. Is that because usually it is more on like a base station side because you're serving multiple clients versus more on the device side? So something like a Starlink dish has beamforming to try and hit different satellites in the sky.
Yeah, well, I don't even think so. For example, so it's always something. It's more advanced because it's either radars, for example, like for cars, right? You have automotive radars. They have beamforming. They have on the right base station antennas. So it's kind of like advanced. If you go into that design, you really need to understand what you're doing. You're doing, kind of. So it's not kind of consuming electronics, I would say. Like, in our mobile phones, we have already some millimeter waves. So millimeter waves are slowly coming now to, we have now 5G, and there are two types of 5G. Normal 5G that is just faster than 4G, and then like super 5G that is millimeter waves. And several years ago, when we were very hyped for this millimeter wave 5G, everybody were talking about that. Everybody were like planning what we will do, like we will stream our holograms or whatever with this 5G. But now nobody talks about that anymore because everybody got just disappointed. Yeah, because it's very, very, it's completely different technology. It's completely different frequencies. It's
Wasn't it also like you needed to have, because of the distance of the millimeter frequencies and stuff like that, you basically needed to have a network like on every light pole so that you're not hopping towers now, you're hopping light poles.
Because why we use this low frequency now in cellular communication? Because they go like, they don't care about shit on their way. Like they go, so
walls, no big deal.
Yeah, exactly. They don't care. They just go and go and go. And millimeter wave, they care about everything. They care about rain, fog, walls, of course, everything. And because it's such a high frequency, so for example, we are talking about 30 gigahertz compared to 600 megahertz.
Right.
So it's
some scale
like
differences there.
Yeah, it's scale difference. And but what you can do is these frequencies are much faster, and if you can have this mesh, then you can get really big benefits from that. But yeah, it's very expensive. That's why everybody were like buzzing about that. But then people calculated what will it cost, and everybody were like, well, actually, maybe not.
All the carriers are like, well, maybe we'll just lean on our existing infrastructure for
lean on our
existing
infrastructure, because updating, well, that's what I do now at my work. Updating from 4G to 5G, easy.
Yeah.
Well, I mean, of course,
a lot of it is software, right? Too, isn't it? Isn't it like software differences?
But also it's still new frequencies, some frequency bands.
Oh, sure.
You still need to update antennas. But it's very comparable to what you have now. If you want to update to millimeter waves, it's completely, everything's different.
Yeah,
cables
it's like changing
are
network
different.
Architecture and all that stuff.
Cables, everything. It's not just antennas; it's all network, the whole network. And and then of course you also need to think that the obstacles, they will destroy the signal, but also just pure air will destroy signal. So it will go like 1 meter and then nothing. So you really need mesh of these base stations. and then you
Maybe it's
have
easier to
very
just
good.
learn how to change the weather. Maybe that would probably be the best way to do it, huh?
Yeah, or like
Beautiful
just
day every
suck off
day.
all the air and have just vacuum. It will make it a bit better too, but still. So yeah, it's now everybody talking about 6G. So
Yeah.
that's the next big thing. But well, 6G it's even higher. It's terahertz that we are talking about.
Oh my God.
It's
Yeah.
much higher. But of course, it's not in the same sense. So it's not nobody talking about like actually building base stations or whatever for that. It's
Got
a
it.
bit
Got it.
different applications.
Yeah. There's a lot of hype built into that stuff, I feel like, and I just kind of ignore. I'm like, I'm still using, if I could still buy the modems and the towers are still turned on, 2G is fine for most of the, like sensor things, and aside from the power needs on the device side, 2G
Yeah, but
bandwidth wise is fine.
yeah, true. But for example, here in Europe, I don't know how it's over there, but here in Europe, they switch off all the 2G,
Oh
3G
yeah. Oh yeah.
networks.
Yes.
So you don't even have now
It's gone. Oh, it's
like
gone. I
that
think the
now.
only
Yeah.
place that 2G is still around is I think some places in Africa still have it because it's like really embedded in some of the infrastructure stuff there. But often it's still fallback. They have 4G, but then 2G fallback is common on a lot of cell devices that I buy. So yeah,
Yeah.
it's no, it is no more. All
No,
those
no,
SIMCOM
no.
modules, they're dead in the water.
I mean, from some point, I like it kind of because I really like the technology, and I
Yeah.
maybe a bit. Sometimes I like this a bit of kind of like harsh push, because if you
Got it.
don't push, then
Yeah.
companies they will just
Oh yeah.
prefer not to do anything,
That's
just
right.
like
I
be in
agree.
this very chill, safe zone, right?
Yeah.
But
Well,
if
it's
you
the money
push
making
a bit,
zone,
yeah,
really, right? I mean,
exactly,
that's what it
money
comes down
making
to.
zone.
Yeah.
Yeah, right,
Yeah.
right. But if you push a bit, like with these
Mm-hmm.
things, I guess it can be really irritating, and so in the beginning, but then it usually leads to some good things.
Yeah, I agree. Okay, so I mentioned multiple times about your simulations that you share and things like that. When should I start simulating? When should I make these beautiful diagrams like you do? Is it worthwhile to learn that as a skill set for any engineer? When should I start looking into that sort of thing?
When you have several $1,000s for a license for
Got it. Yeah, just
but I
money
mean,
jingling in my pocket.
I mean this simulation software is very expensive, but there are several open source softwares.
Okay. All right.
So that's very good. Community is quite good on this in this area. Well, in all engineering area, you always have some like open source things, but in this
Yeah.
also we have some like open source, at least two software that's been developed and currently like supported by community. So yeah, you can try that, and you don't need money to buy licenses and so. Well, I don't know. I don't. I think if you want to try,
what are those two pieces of open source
yeah, I
software?
think that's a one called EMC. So EMS.
Oh, SEE.
Yeah.
Yeah.
So not EMC like electromagnetic compatibility, but EMS. So yeah, so yeah,
Yeah,
like
like visualizing
one.
electromagnetics, right? Like so
Yeah,
seeing
exactly.
electromagnetics. Yeah.
Yes,
Okay.
yes.
Okay.
So one it's called like that, and just open source.
Okay.
And another one, some I don't remember now, like off the top of my head, but some strange name.
Okay.
I remember the first one, and yeah, so it's like it's like key card.
Yeah.
It lives only by like support from the community, kinda. So you solve everything together.
Yeah.
So
And even
yeah,
there, I feel like there's so much like of a graphical component. So I use FreeCAD, I use KiCad. The graphics are great and improving, but that feels like the hardest part, like the actual solvers, like the mathematical solvers, but then the visualization on top of it. That feels like that's the thing that people are often paying for.
yeah.
Like
To be honest, like in this antenna design, this visualization, it's mostly like a kind of plane around. Yeah, with all the animation that I share, I don't really need them. Like
Oh,
really,
interesting. Okay.
I don't
So maybe
really
you could tell
need
us
them.
that what's that push pull then? So you share these visualizations, which helps newbies like me in this scenario, but how are you using it differently then in terms of your design work and
Yeah, I
actual
basically
output?
I simulate the same things, the same metrics that I will test later.
Okay. Okay.
So I simulate this return loss matching to the impedance. I try
Hmm.
to optimize that, and then I try to optimize the efficiency. But sometimes, of course, you want to, for example, see how fields go, especially in the beginning when you, for example, when
Yeah.
you're a
Yeah. Yeah.
student, you want to know, okay, but like fields go there, and then maybe I need to put somewhere something there, or like some shielding or whatever. But when you already kind of know most type of antennas, and then you already know like what it will be, and you don't
Mm.
like, if I design by myself, like actually my work, actually my project, I never plot these fields or
Got it. Yeah.
or
Yeah. Yeah.
like
That makes sense. Yeah.
animations. I
Sure.
don't do that. Well, maybe like one case out of 100 when I'm really confused or troubleshooting or trying to understand what's the
Mm.
problem, what's
Got it.
there, like some resonance
Got it.
happening, for example, and I cannot understand. So then it might help to plot some fields and see what's happening. But usually it's all numbers. It's all numbers.
Got
It's
it.
it's much
Yeah.
more boring than than a show on
No, no, no.
LinkedIn.
That's a great thing because, like you said, I mean, I expect the antenna engineer is doing that visualization of fields, but it's not as practical because, like we were talking about with the anechoic chambers, you don't validate against that either, right? It's not like you can go and visualize and be like, oh, well, look, this
Yeah,
this lobe's over here. It should be over there, right? It's like, no,
yeah.
that's not how it works. Yeah. Okay. What about like the iteration? So you get tasked to go redesign an antenna. How do you know what to change? Like, what are you
Uh,
tweaking in terms of geometry of the
yeah.
antenna or
So
capabilities?
yeah, so for example, you kind of come from what you know is wrong. For example, if the frequency is wrong, so for example, like working frequency shifted, right? So it's supposed to work on 2.4, but now it works on 3 gigahertz or 2
Yeah,
gigahertz.
yeah,
Then you know that it's size of the antenna, because the size of the antenna dictates the frequency, working frequency. Then you can start to maybe make it smaller, make it bigger, depending on where your frequency shifted. Then what if the problem is in like you see that you have much more reflections, then you start to think of, okay, so my signal from the chip, from the PCB, it reflects somewhere on the way to antenna. So how can I solve it? How can I, maybe my trace is too bad, too narrow, too wide, maybe I don't have good grounding, maybe I have bad matching network for the antenna, and so on. So then if you have several antennas, you can much more like challenges coming from that. You can have coupling between these antennas. Then you also need to see how they couple to each other, like how they affect each
hmm
other, and maybe separate them further, maybe like put them further away, maybe like turn one antenna 90 degrees to so they placed orthogonally, so you have some like polarization diversity. Yeah,
Mm,
it's just kind of like, you if you need to troubleshoot, then you start from the problem.
got it. Okay. I had done some RF stuff. I was starting to get into a little bit more. I had an 8753 in my old lab, and I'd be looking at Smith charts and
Mm.
moving my hands near an antenna, and I'm just like, I don't know what's changed. I it was always tough. So one of our longtime guests on the show, Jeff, he would be like, "Well, you got to kind of go back to first principles and understand that sort of stuff." And I'm just like, "Yeah, but I'm just waving my hands, and the Smith chart is just bouncing all over the place." And so
Oh,
it was
of
really hard
course,
for me to like
because
back
of the
calculate that.
yeah, human body,
Yeah,
as we talked before, it's very, very, very
yeah,
harsh.
yeah.
Yeah, so well,
So
Smith chart is the great tool if you
mhm.
understand what's what's going on.
Yeah, yeah. Right. So yeah, and maybe that. So you said troubleshooting. So maybe could you lay out the tools that you use when you are in a situation where like this antenna isn't performing as expected, and you have simulation at your disposal, but maybe like other troubleshooting elements that you use to then back calculate what might be the problem.
So if it's already a prototype and I see that it works not as I would expect, then it's usually something with the matching.
Okay.
And then you usually, I don't know, like maybe for very simple antennas you don't even have some matching network, but usually you always put at least like
Yeah.
2 3 components
Yeah.
of
Yeah.
matching network.
High
And
filter just to
yeah.
put the shape in, and you're in good shape. You're
Yeah, so and you usually start to looking into the matching network and try to match it better.
Okay. So you're saying that you're starting from a prototype of an antenna, and you know that that is working because you've done measurements on that in the lab
Mm?
and such. But then I guess, how do you know that the antenna was right in the first place as well? So you've been, just to back to the beginning of the episode, I suppose we were talking about, you start with a block of a PCB in a vacuum, whatever. You start adding things like a squishy human hand into the picture, and you start simulating around it, and you also change the shape or the characteristics of the material itself. But then you know that you have a hand holding an antenna now, and that's performing as good as you need it to, because why? Like, how do you know that that's good enough?
Well, so it's kind of feeling. So
Okay.
you have, of course, you have all your metrics, right? You can see radiation pattern
Okay.
in the simulation. So if we're talking about like first steps, you can see the simulation pattern, and based on that simulation pattern you want in the end. For example, like if you're talking about headphones, we put it in our
Sure.
ear, and we really don't want blast signal in the head.
Yeah.
What we
Right. Right.
want
It's like
is
wasted
to
power.
have signals outside the head, and that's how you can think, okay, I need this kind of radiation pattern, right? So it goes like in this direction and not to that direction. And
Okay.
because
Yeah.
you know like different types of antennas, you know which type of antenna will give you approximately that. So
Got it.
you at least kind of start with that. Okay, I need this type of antenna.
Yeah. And that's
And
like a
then you,
topological choice of like
yeah, the
monopole, dipole, that sort of thing, right?
yeah, a topological choice, and also like the principle, right? So some antennas
Yeah.
work differently. Some antennas like
Yep.
only directional, some antennas are directional, some antennas work over the ground plane, some antennas doesn't need ground plane below it. So you choose this, and then of course you have restrictions of your environment. So you start to put this antenna that you chose. You know that this antenna, like in ideal world, for example, it's like 100 millimeter straight wire. This is this antenna like it in its prime, but then you need to put this like in such a shape that it will fit into your device.
Got it. Yep. Okay.
Yeah, and then you have radiation pattern, you have efficiency, you have all the like numbers, right, in the simulation that you're looking for. So for example, you know that you want 80% efficiency, that you want this radiation pattern that radiates outside the body, not towards the body. You want to have good matching, you want to have good return loss, not no reflection back to the PCB. Yeah, that's how you understand that this is antenna that fits this application.
Got it. Yeah. Yeah, and I guess like you said, I mean, we're really talking about like almost like a spec sheet that you would have been handed, or working
Yeah,
collaboratively with a
specs.
mechanical
Yeah,
engineer to do
spec
that
sheet.
sort of thing. And then
Well, yeah, usually you almost always you have some specification. For
yeah,
example, how much gain you need, how much efficiency you need, what size restrictions. It's always some size restriction, unfortunately.
yeah.
And then like weight.
So if you had your choice, you would have like just a car-sized PCB for the ground plane, that sort of thing.
Yeah, just in a vacuum, like no people
Uh-huh.
around, nothing
Uh-huh.
around, just
Yeah.
antenna, like
Just the easiest,
yeah,
spherical
easiest,
cow emitting
easiest, yeah,
RF in all
exactly,
directions,
and
right?
just blasting in all directions. Yes.
Yeah, totally, totally. Yeah. Wait, so is satellite design easier or harder than, I don't know, ground?
The satellite design is, well, we have a lot of antennas on satellite, so it's very
Sure,
different.
yeah.
They also have also now they have like millimeter waves. They have
Oh, sure.
higher
Yeah.
frequency, like lower frequency, higher frequencies, and they have this dish that's very high gain, because you need very high gain to reach longer distances. It is like, as an antenna design, it might be not so complicated, but it's such a harsh environment. Imagine all the vibrations, imagine all the risk there, like weight restrictions. You cannot just like take 10, 20, 30 kilograms like of the metal and just shoot it up the space. They have very harsh weight restrictions, they have very harsh temperature so requirements, right? It needs to work perfectly at minus 100 and plus 100 degrees. And
Right.
so it's very harsh environment, and that's why you only kind of use only like restricted amount of antenna types that can survive this.
Yeah, that seems like that would be, and then of course all the radiation coming from the sun, I'm sure, is also
Yeah,
not
yeah,
great.
yeah, and
Depends how
you
close you
really
are,
need
right? But
very like very robust, like
yeah.
very robust, very antennas that you can trust that they will work a long time and in this very harsh environment, yeah, in all the radiation, and because there are a lot of satellites there and a lot of kind of like signal pollution as well.
Mm,
So yeah, it's very harsh in this sense, like to actually get your antenna work in the environment.
mm. I don't think I have any chance of designing a satellite antenna anytime soon, so I'm probably going to stick to more of the. When I think about this sort of stuff, the designs I'm personally, yeah, I'm gonna go personal here. The stuff I usually do, like I said, is usually offloading to someone else using a UFL connector or something like that. Maybe putting antennas on the PCB once in a while for 2.4. Not really. I don't really plan to do anything. And then like probably the extreme low cost case would be adding a coiled antenna to like a LoRa chip or something like that, or a wire. That's about as far as I'm going to go. And I have very low expectations. That's just to try it out. And then like I expect it to go across my desk as opposed to operate in the field in harsh environments, that sort of thing.
Yeah. But I actually think that to have this connector for an antenna, it's usually if you can afford that, right? Like, if your
Yeah,
device
right.
can afford to have antenna outside of the device, that's always better than to have PCB antenna.
Okay, that's another good rule to have there. Does it matter then? The ground plane size still matters though as well, right? So
Still
even if you have a
matters,
super
but
tiny
it's
device.
less. It's more forgiving in this case
Oh, it
because
is. Okay.
because the antenna size also will be bigger.
Got it. Okay.
So, but it still matters. It still needs ground plane, but it's more forgiving that antenna that embedded in the PCB.
Okay. All right. Yeah, I've used a lot of those like flex antennas in the past as well. They're okay, but it does
Yeah,
also seem like sometimes it's directionality. Like if I try and shove it inside a plastic case with all the other stuff that's going on in there, it's maybe not the best idea, sort of thing.
yeah. Flex antennas can be good, but they also you can break them very easy.
Yeah.
So
Right.
the antenna itself, okay, is supposed to use like that in this way that it's bent one time and you just keep it like that's this way.
Yeah. Right. Right.
If you
Don't go
open
flexing
your
it and
case,
stuff.
yeah, exactly, flex and all these things, and it can get broken. Then of course the connection to this antenna as well, like how to feed antenna, it also can be a bit tricky. And then you really need to think in this case about the material of your case, because antenna
Okay.
is flashed to that case, and that case is dielectric, and this dielectric has dielectric constant.
Okay.
Usually it's some plastic, so the dielectric constant not so high, like 2.4 or so, something like that. But sometimes you have some like resin in plastic. Sometimes you have like some fancy
Yeah, like 3D
cases.
printed enclosures and
Yeah,
stuff like that,
exactly.
right?
And then dielectric constant can get really high. And if you remember, we discussed that before. The electric constant change the antenna working frequency. So that can also affect antenna a lot. So you need to think about that. That also works for PCB antenna. That works for all antenna, like everything that is in the near field of the antenna kind of affects antenna. So the enclosure of your PCB antenna also affects antenna. But usually we don't maybe spend too much time on that because it's already you have so much challenges, people already tired from that. So
Yeah.
you try to maybe
Yeah.
like at least to minimize that. But like if we honest, that also should be taken into account. But if we're talking about like most common plastics, they are not so high in the electric constant, so that's why like it's forgiven. But if you happen to have some very fancy material, like some resin or something like that, then you out of sudden you see that your antenna doesn't work as you thought, even though you have good clearance, you have good PCB size, you have everything. But then you put it into your case and it doesn't work anymore because the electric in the case shifted the working frequency.
Yeah. Well, and then people need to give you a call and help fix it up. But that's probably where we should leave it because I've already taken a lot of your time. I really appreciate you walking me through. I mean, like, it feels like I could study this for years and years and years. And it's a very deep field, it feels like.
Yeah, I think so too. I've been working now soon 10 years in this. And then before that, university, of course. But so 10 years. And yeah, I really feel still that I learned so much, especially when you work with people who've been in the field for like 40 years, and and you like look at them, and they like these kind of like super creatures who have
galaxy
like,
brain.
Exactly, they have answers for everything, and you feel like you only on the surface.
Yeah. Well, I mean, that's great. That is one of my favorite things about electronics, is just there's always more places to go. And then obviously the field keeps accelerating away from me. So I'm like, yes, more space to run. It's great. It's also a little frustrating maybe, but then I get to talk to brilliant people like you and learn from that. So where can people follow you online and see all these simulations I've been talking about?
Yeah, it's my LinkedIn. I guess they can find me by my name or by some links that you can provide. Just Katerina Galitskaya on LinkedIn. I think that's it's quite easy to find.
Great. Yeah, we'll definitely link that in. Katerina, thank you so much for being here and explaining this stuff. And I'd love to chat again with you in the future.
Thank you very much for having me. Bye-bye.